Dimensionality of derivative. Consider a function. So what is derivative? Derivative of a function with respect to something else. So when you have a function with respect to a variable, before you read about this slide, listen to what I'm saying. This because I want to explain what derivative is. See, when you have a variable and you have a function, the derivative of that function with respect to that variable means that whenever you change that or tweak, you slightly change that variable, how much the function changes. Do you understand what it means? So how much effect the change of variable has on the function? Okay. Whenever I move that function a bit, how much effect it has on the function. This is the derivative of that function with respect to, or WRT with respect to that variable, right? So now assume the function is D2 dimensional and the variable is D1 dimensional. The derivative will be a matrix D1 by D2y, I tell you. I think by these examples, it will become clear. First, assume the variable is a scalar. I think it needs to be variable. I will correct this. The variable is a scalar. And okay, assume the variable is a scalar. F is also a scalar. What happens? It means that the function is a scalar output. The input is also a scalar. Whenever I change this input, it changes the output. Therefore, the derivative is a scalar too. The second example, I think, clarifies it better. Assume that now the x, the input, is a vector, and the function is a scalar. What would be the derivative? When we say the variable is a vector, it means that when you change every element of the vector x, it changes it has some impact on the function f. It changes the scalar f, right? So assume that x is a three-dimensional vector. I think with this note, it becomes clear to what I mean. Assume x is 1, 2, 3, and the function of x is a scalar. For example, x transpose x, right? It's a scalar. Now, whenever you change the first element, this epsilon might be positive or negative, and you don't change the other elements. This changes f. Now go to the second element, change it a bit, and don't change the other elements. This also changes f a bit. Do it for the third element. For every element, you change it. This changes f too. Is that correct? Now you tell me. So you have three options for changing x because it has three elements. And 3 times you changed f. Therefore, the derivative is a three-dimensional vector for each of these changes. This is for here, this is for here, and this part is for here. So when the output is now, the first example was when it is a scalar, and the output is also scalar. Whenever you change this, for example, it changes f. Therefore, the derivative is one-dimensional. You have only one case where you can analyze, only a scalar. Let's go to the next page, another note. Assume x is three-dimensional, 2, 3, 4. F of x is also a vector. Assume, let me think. For example, this is x1. By x1, I mean the first element, x2, x3. Assume it is a vector where x1 plus x2, and this is tangent of x1 squared, x3 squared. So the function f is 2-dimensional. The input is also 3-dimensional. Clear? Now, so this is 2D. This is 3D. I want to see what is the derivative of f with respect to x. What's the dimensionality of the derivative? So the dimensionality of function is 2. The dimensionality of input is 3. Now let's see. First, I change the first element. It changes. Let's call it f1. The second element of f2. It changes f1. It also changes f2. It might change. The change might be 0. For this case, the change is 0. But it in general case, it might change, right? Also, now I go to the second element of x. I change it. I think if for you to understand what I mean, let's make it more. I want you to understand what I mean. Assume it has all of these cases. So this is f1, this is f2. Now, this changes f1. This also changes f2. Go to the third element. Changes f1, changes f2. How many cases could we analyze? So every element the change of every element of x will change or tweak every element of f. 1, 2, 3, 4, 5, 6. Six cases. In other words, 3 cases for input, change of input. 2 outputs we have, 6 cases. Therefore, the derivative will be 6-dimensional. This is what derivative means, that by changing the input, how much effect we have on the output, right? So, and we usually denote derivative with this partial f of x with respect to x. This means that derivative of f with respect to x. This is 6-dimensional. Sorry. This is 6-dimensional, but there is a but here. We usually show it. We don't vectorize it. We usually show it by a matrix of 3 by 2. We can vectorize it and it becomes a 6-dimensional vector. But we usually have 3 rows and 2 columns. Why? The rows correspond to the number of elements of x, and the columns correspond to the number of elements of f. So far clear? Is it obvious? Any ambiguity?
It's clear.
Sorry, what did you say?
I said it's clear.
Okay, great. Thank you. So, in other words, the derivative of a scalar with respect to a scalar is a scalar. In this example now, the derivative of a scalar with respect to a vector is a vector. The derivative of a vector with respect to a vector is a matrix. Rows for the vector of input, columns for the vector of output. Now you tell me the derivative of. So here we had derivative of a scalar with respect to a vector. We might have a derivative of vector with respect to a scalar. When, for example, this is an example. We might have this example. X is a scalar, however, f of x is a vector. X and x2, right? This input is a scalar, output is a vector. So the derivative of this is a vector. Derivative of a vector with respect to a scalar is a vector. Derivative of a scalar with respect to a vector is also a vector. Derivative of a vector with respect to another vector is a matrix. Can someone tell me the derivative of a vector with respect to a matrix? What is it? So this is an example. If you understand this, you understand what derivative means. 2, 4, 5, 6, 7. This is a matrix. And assume this, but this is x1, 1. This is x2, 3, xij, I mean. So now assume the function is x1, 1 squared, and I don't know, summation of I1 to 2 x I3 squared, something like that. I want to say that this function is a vector. The input is a matrix. We can have different cases, right? So this is a 2 by 3 matrix. This is a two dimensional vector. What is a dimensionality of f of x with respect to x? Can someone say that? If you say this, so go with my example. What you tweak every element of this x and see the effect on every element of f, right? So what will be the derivative? How many cases will you have? Can you tell me how many cases? First, answer this question. How many cases will you have? This has 2 by 3, 6 values, right? 2 by 3. This has 2 values. How many cases do you have? Can someone say that?
12.
Exactly, 12. We have 12 cases. But we don't want to vectorize it. We don't want to represent it as a vector. We want to have it as a matrix format. So we know rows are for these, columns are for this, right? So the dimensionality of this will be what? Can someone tell me? This will be 2 by 3 by 2. 2 by 3 is for this, 2 rows and 3 columns of x, and this 2 is for this. Is that correct? So it will be a tensor. It will be a 3-dimensional matrix. It will be a cube, like a cube. Matrix is a 2-dimensional thing. It has rows and columns. And then you also have a height. Do you get my point? Is it clear now what I mean by the dimensionality of derivative?
Yes.
Yeah. Do you remember in the, I think it was in the previous lecture, previous session, that we talked about the dimensionality of derivative? Do you remember? So now there's another thing. Now how to calculate the derivative? So we know we have discussion for we had the discussion for the dimensionality of derivative. And now let's see how to calculate that. So one way is to assume you see such thing. Okay, without dimensionality, even you don't know the dimensionality of A, X, B. So you have derivative of trace of A transpose X, B with respect to X for any dimensionality that they have, but they are matrices. Okay. Likewise, we can have the same discussion for vectors. And one way to solve this is going through the matrix cookbooks. There are 1,000 pages. You need to go and find this specific derivative among a lot of pages. And okay, so you can see it as a formula. However, I'm going to teach you a technique which makes you needless of these cookbooks. Okay. And I came up with this during my PhD myself. So this is a technique. Assume I said derivative of this trace of A transpose XB with respect to X. We know that, so it's what is the output of trace? The dimensionality of output of trace is 1, right? Because the trace's output is scalar. Agreed? Trace of a matrix is a summation of its diagonal elements. Okay. With respect to X is the matrix. So derivative of a scalar with respect to matrix becomes a matrix as discussed in the previous session, right? So we know that derivative of a scalar with respect to matrix must be a matrix. And what about its dimensionality? Whatever dimensionality X has, the derivative must have also. Do you remember why? Let me recall this again briefly. So what was the definition of derivative in high school? Simple one. Derivative of Benjamin with respect to desk is, what does it mean? Change or tweak the desk and see how much it impacts Benjamin, how much Benjamin changes, right? So as a result, derivative of a scalar with respect to a scalar is a scalar because you tweak that scalar and see how much the other scalar changes. Derivative of a scalar with respect to a vector becomes a vector because whatever elements that vector you change, it will have impact on that scalar. Also, likewise, derivative of a scalar with respect to matrix becomes a matrix with the same dimensionality. Okay. Now let's see how we can solve it. So we know the result must be a matrix. And now I don't have a dimensionalities, but I assign fake dimensionalities to that. Okay, fake dimensionalities. Then usually try to, if possible, if mathematically possible, try to assign rectangular dimensionalities. Why? Because if you say X is a square matrix, for example, 2 by 2 or 3 by 3, then you don't know which 3 it is later when you calculate. The left 3 or the right 3, right? So here I say 2 by 5, so I can distinguish between 2 and 5 easily. If mathematically makes sense, sometimes you have to use the square dimensionalities. Okay, and if it was a vector, then I would say 2 by 1, for example, right? So it's 2 by 5. Then this is 2 by 5, this X in the middle. So my A transpose should be something by 2 because of matrix multiplication, right? A transpose X. X is 2 by 5, so A must be something by 2. Let it be 3 by 2. As much as possible, let them be rectangular so you can distinguish them. 3 by 2. You have, I don't say 5 by 2 because I don't want the 5 of A to be confused with the 5 of X. Okay? So I have 3 by 2 and 2 by 5. Now also this one, X by B, X times B. X is 2 by 5, so B must be 5 by something. But what thing? Can I say 5 by 7? No, do you know why? Because the whole thing becomes 3 by 7. The whole A transpose XB. And I know that the input of trace must be a square matrix. Okay? So as A transpose was 3 by 2, B must be 5 by 3. So the whole thing becomes 3 by 2 times 2 by 5 times 5 by 3. So the whole thing becomes 3 by 3. Did you see how I assigned fake dimensionality? Now let's use these fake dimensionalities. You tell me, trace of A transpose XB with respect to X, is it linear, quadratic? What is it? With respect to X. This function of trace of A transpose XB, is it linear with respect to X, quadratic with respect to X, whatever? You tell me. Forget this. AX plus B with respect to X. Is it linear? Because I have X here. AX squared plus B is quadratic with respect to X, right? Now in the area of vectors and matrices, when you see X once, it's linear with respect to X. When you see X twice, it's quadratic with respect to X. Agreed? So here I have one X, So it's linear with respect to x. And usually the format of the formulas that you memorize for derivative works for even matrices and vectors. I mean the format. What do I mean? For example, what is the derivative of x squared with respect to x? 2x. As a result, derivative of x transpose x with respect to x also is 2x, where x here is a vector. So the format of formula is the same. Okay. Derivative of ax plus b with respect to x becomes a, the multiplier of x, right? What are the multipliers here? There are a transpose and b. As a result, the result must be one of these cases. A transpose b, b transpose a, b, b transpose, ba transpose. Maybe one of them should be transpose times the other one. The order changes. Let's see one by one. Okay, by trial and error. A transpose B. So it's according to these fake dimensionalities. It's 3 by 2 times 5 by 3. That nonsense mathematically. B transpose A, 3 by 5, 2 by 3. Nonsense. AB, 2 by 3, 5 by 3. Nonsense. BA, 5 by 3, 2 by 3. Nonsense. AB transpose and BA transpose. So AB transpose is 2 by 3 times 3 by 5. So it becomes 2 by 5. Makes sense mathematically. BA transpose, 5 by 3 times 3 by 2 is 5 by 2. Makes sense mathematically. The dimensionality of x was 2 by 5. Derivative of a scalar with respect to a 2 by 5 matrix must be a 2 by 5 matrix. So this is the true answer. If you go to the cookbooks, you'll see this. Okay. Now, one might say, also, I can see the derivative of a scalar with respect to a 2 by 5 matrix. Let it be 5 by 2 matrix. So basically transpose it. I will answer you, yes, you can do that. But if you do that, you should transpose everything in your mathematical expressions. You should transpose all of your matrices. If you do that, then you can do it. It makes your world harder. Okay? If you want it to be easy for you, let the dimensionality of derivative match the dimensionality of what we're taking derivative with respect to. Okay? Otherwise, feel free to use the transpose, but you need to transpose everything. So what should we do? How to train? The first thing which comes to your mind. I have some predicted labels. I have some actual labels. What should I do? I should try. The best thing is that my predicted labels become as close as possible to the actual labels. So let's minimize the mean squared error, right? So exactly we are doing this. So squared Frobenius norm between y, which is the actual labels, and y hat is exactly mean squared error, right? Recall preliminaries for definition of Frobenius norm, okay? So we have the actual labels k by n, and the predicted labels y hat k by n, and squared Frobenius norm of between these. Now let's replace y hat with equation 4. So y hat was w transpose phi, right? And what is my optimization variable? The matrix W, right? The weights of the second layer in RBF network. Okay, so now let's simplify this cost. Why? Because I want to take derivative, set it to 0. Because this is also an unconstrained optimization problem. So high school optimization. Take derivative, set it to 0. Okay, first let's simplify this. What is the formula for squared Frobenius norm? Squared Frobenius norm of desk becomes desk transpose desk, but I need to have trace because I need to make it a scalar, right? So trace of this transpose this, right? Which is here. Okay, now I apply transpose on the elements of the parentheses. So it becomes y transpose, and this one transpose. The order changes, is reversed. So I have phi transpose w, and the rest as this. Now I have these two terms multiplied by two terms. I have four terms. So let's multiply the terms to each other. I have y transpose minus y transpose w transpose phi minus phi transpose wy plus phi transpose wy transpose phi. Okay. Now trace is a linear operator, so I can apply it on the elements. Right? Moreover, I can use the cyclic property of trace. You know the cyclic property of trace, don't you? Okay, if you don't know, just let me tell you once, because we use these a lot. So trace of A, B, C, assume A, B, and C are matrices. You can bring every matrix to the other side and do it repeatedly. For example, it is equal to trace of CAB equal to trace of BAC and BCA, and then again trace of ABC, back to where we were. Okay. So this is cyclic property of trace. Now, so here I have used cyclic property. How? I have brought this to this side and this to that side. Equivalently, for simplification, for cyclic property also goes the other way around. So I can say I bring this to the right hand side. Okay. Also here, I bring this to the right hand side. What about this one? For this, I need to do cyclic property twice. So phi transpose w transpose phi becomes phi transpose w transpose, then becomes w transpose phi transpose w. Agreed? So I will have this. Now let's take derivative with respect to w. But so this one is a constant with respect to w, goes away. This one is linear with respect to w, is linear. How do we take derivative? So I think I didn't say this in deep learning course in this technique. Let me say it once. I have said it in the statistical machine learning course. So trace of w transpose phi y transpose. Trace of w transpose phi y transpose. Okay. Let's name this A, matrix A. Trace of w transpose A. Okay. So the derivative of this with respect to w, we know that this is a scalar and this is a matrix. So derivative of a scalar with respect to matrix is a matrix. And we know that this is either A or A transpose, but which one? Which one? Let's see. Here, assume W is 3 by 5. Assume, okay. So this W transpose becomes 5 by 3. A becomes 3 by 5. When then the derivative of a scalar 1 by 1, because it has trace, with respect to a matrix 3 by 5, by convention, I say it must be 3 by 5. You can choose another convention and transpose it. But if you transpose it, you should transpose everything. Okay. My convention is easier. I say derivative of a scalar with respect to 3 by 5 should be 3 by 5. So if I do that, then here A, according to my calculations, as W transpose is 5 by 3, this must be A must be 3 by 5. Therefore, this is acceptable. This is wrong. Did you understand the technique? So I give fake dimensionality to the matrices, and then I see which is correct. Okay. By the way, I can make it more complicated rather than this. For example, assume I didn't name this phi y transpose as A. Then you could say I have several options. The derivative is either phi y transpose or y transpose phi, or you tell me phi transpose y, some of them will be eliminated immediately. Why? Because the matrix dimensions should match in matrix multiplication, right? Some of them are nonsense mathematically. Okay, so they are removed. Some of them make sense mathematically, but how do we eliminate some and take some of them, some other? By these techniques that I told you. Give fake dimensionality to the matrices and check the dimensionality. Even you can use this technique even when W is a square matrix. Still, you can give fake dimensionality. 3 by 5, not 5 by 5. Why? Because if you give 5 by 5, we don't know which 5 it is, left 5 or right 5. Give fake dimensionality differently, like 3 by 5. Although you know, for example, that is a square matrix. Then you can filter out which one is the correct derivative. If you don't want to use this technique, feel free to go and check the derivative in the matrix cookbooks. There are 1,000 pages. And go try to find that specific derivative. Okay. So as I said, the derivative of this became A itself, right? This was A, right? Now, derivative of this using that technique that I told you, this is linear with respect to W, right? So it is this. What about this one? It's a quadratic function with respect to W. So its derivative with respect to W must be 2 phi transpose W, right? And now set it to zeros. 2, 0 matrix, right? Because derivative of a scalar with respect to matrix is a matrix. Okay. Now rearrange the terms. So we know that these are equal to each other. So it becomes minus 2 phi y transpose. And the 2's cancel each other. 2 2's cancel each other. So we'll have this. Agreed? This is a pain in the neck. Because I want W, right? Left multiply the sides by phi transpose inverse, by its inverse, to get rid of that. Then you will get this. Agreed?